Welcome to ECS 721 course on data structures and algorithm, and this is week number 4, lecture number 1. Let's dive into the agenda for this week. And agenda for this week is going to be, we'll focus mainly on the following two major topics. The first of these is asymptotic notations. There are 3 forms of the asymptotic notations, and we use these notations to measure the running time of an algorithm. We're going to see in details how we do that in today's lecture. Then after that, we are going to talk about the stack data structure and its implementation using linked list and arrays, and then we'll contrast and compare that which implementation is best in which circumstances. So let's dive into the lecture. So what is an algorithm? You are already familiar with it. We have actually been executing algorithms in our daily life regularly without being realized that it is an algorithm. So algorithm is simple, a set of steps to accomplish a task. It's as simple as that. It's a sequence of steps that we perform to do something. It's like a recipe in a recipe book. When you want to cook a particular meal, you have the set of ingredients and then the set of steps that you perform in order to cook the meal. So you might have an algorithm for getting from home to school. It's very, very abstract, but it does convey the message that there are a set of steps, like you have a bike and you go to the station, you take a train, and then you walk to the school. If you change this order, this algorithm may not work. So this is the algorithm, a simple one for a kid that who goes from home to school. For making a grilled cheese sandwich, you acquire the bread, you apply the cheese, you grill the sandwich, and this is another algorithm. Similarly, for finding what you are looking for in a grocery store, you might find the right aisle. It's like a cupboard that are placed in the store, and you scale from top to bottom, left to right, for the item you are looking for, and once you find the item, you stop there. So this is an algorithm. It's very abstract, as I said. There are a lot of details we could add to this algorithm, but it does convey the message that an algorithm in its simplest form is the set of steps that you perform to achieve something, right? But remember, when we write algorithm for the computer to execute, we have to be very, very precise, because the computer, after all, is a dummy machine. It doesn't know anything on its own. It must be instructed precisely to do something. And for example, if you write an algorithm and the computer executes the algorithm and it doesn't give you the result, that's not the fault of the computer, but that's because the algorithm is incorrect. So algorithm might be correct or might be incorrect. A correct algorithm will always produce the same result for a different set of inputs. An incorrect algorithm might behave differently for some set of inputs. There are a few famous algorithms I just wanted to touch. The first is the Google Hangout, which is an application that transmits live videos across the internet, but they do it in a blazing fast manner, and that's because they are using the compression algorithm behind the scene. Similarly, a Google map will guide you if you want to find a route from your source to destination. For example, let's say we want to go from Noshera to Islamabad. It's gonna draw the route, and how does it do it? Based on the route finding algorithm behind the scene. Similarly, NASA has solar panel on the International Space Station, and when to arrange those stations, for example, they are using the optimization and scheduling algorithm. So these were some of the famous algorithms I just wanted to talk about. Similarly, the Google search engine used the PageRank algorithm, and if you want to search a keyword in Google search engine, you type the keyword, you hit enter on the keyboard, and what happens in a fraction of a second that you get the list of website which contains information about that keyword. How does the Google search engine list some of the websites which contain your word that you're looking for on the first page? So they are using behind the scene a page ranking algorithms. So the line that's very important on this slide is avoid reinventing the wheel. You don't have to design your own algorithm all the time. For example, if you are working on a software system and you have studied different algorithms for sorting, for example, for searching, you can just pick one, and you have to, of course, analyze which one is faster and then use that in your program. So you can save a step and do something, quickly. Now let's talk about the main topic for this lecture, and that is how to measure algorithms. It's very important that you pay attention to this. If you don't understand something, you might study this in much more details in a course called Analysis of Algorithm. But I just wanted to give you an overview that how do you actually measure algorithm. So a naive way to measure the running time of an algorithm is using a stopwatch, but of course that depends on a lot of things. For example, the speed of the processor in the computer, the compiler, how optimized that compiler is, how long does it take to convert the source code into the object code, and among other factors. So we want to come up with a hypothetical machine. They usually call it RAM, which is the random access machine. Do not confuse this abbreviation with random access memory. It's a random access machine. It's a hypothetical machine. That means that each primitive statement, no matter in which programming do you write it, because algorithm after all are programming languages independent, so it is going to take a constant time, right? It has a single processor and a single piece of memory, and there is no problem with the size of the RAM in the hypothetical machine. So let's think about the running time of an algorithm more carefully. There are two ideas we are going to need to put together in order to achieve the task. The first one is we need to determine how long the algorithm takes in terms of the size of its input. It's very important that for different sizes the algorithm behaves differently. And the second idea is what we must focus on is that the most important part, how a particular function, I mentioned the word function because we represent the running time as a function of the size of input. So how fast the function grows as we increase the size of the input on which the algorithm operates. So we call this particular concept that the second line, the second idea, the rate of growth, or sometimes it's called the order of growth of the running time. That simply means that if you gradually increase the size of the input, how does that particular function behaves, or how fast does it grow? So for example, suppose that an algorithm running on an input of size n, take this particular line is an equation 6n squared plus 100n plus 300 machine instructions. Remember, we do not measure the running time of the algorithm using the actual time units, but rather the number of steps that are involved in that particular algorithm. So these are actually machine instructions. And how do we derive such a function from a code? We're going to look at the end of this particular lecture. So this is an important thing. This is the representation that there is a piece of code, and we have derived this particular function from that code. And now we want to talk about the running time. So 6n squared term in this whole function becomes larger than the remaining two terms, which is the 100 and n plus 300, when n becomes large enough. In this case, 20. I'm going to show you the chart, but just for the moment, n, whenever I mention the word n, it means the size of the input. So think of it as the size of the array in order to make it simple. So as you increase the size of the array, searching is going to take longer, right? And if the size of the array becomes very, very large, then you will notice that the term 6n square dominates the other two terms, 100 and 300, and actually this is the term which is contributing more to the growth of the function, overall function. So chart on the next slide showing values of 6n square and 100 and plus 300 for values of n from 0 to 100. So let's talk about this slide, and what's the x-axis represent the size of the input, right? The x-axis is the size of the